and good morning everyone. I welcome you all to India's largest e-learning platform, Unacademy, and I welcome you all to my session of Antennas MCQ series. Welcome you all to Conqueror channel. Just kindly confirm the video and audio once. Kindly confirm the video and audio once. One second here. Good. One second, just a second. It seems to be good. Now just confirm once. Just confirm once. Someone please confirm. Seems to be okay. It looks good, looks good. Thank you, thank you. So I welcome you all to the Antennas MCQ series. This is part 11. Very interesting series, dear. This series will be useful for all those who are preparing on antennas, for all those who are preparing for competitive exams, where antennas is a common syllabi. For all of you people, it will be very much useful. Hi, last day, hi. How are you? How are you, dear? Before we start the session, let me introduce myself. I am GC Reddy, having 15 plus years of experience in teaching, guiding and mentoring GATE and ESC aspirants. I work as motivational speaker, pan-India from the past 12 years. Expert in field theory and communications. Before we move in, let me introduce our Telegram channel, the GATE Conqueror channel. This is the link where you can join us on Telegram. Once you join us on Telegram, you'll get the personal access to all the faculties of the GATE Conqueror channel. We will be very much happy to help you all. And the good news for all the GATE Conqueror followers is that we are increased in numbers now. Some more new faculties, very talented, very energetic and very famous faculties are going to join us, and very soon they will also take the YouTube classes, and we are very much determined to complete GATE 2023 syllabi comprehensively. Along with that, engineering services 2023 syllabus comprehensively. So Today also I'll try to explain how comprehensively we are trying to cover the syllabus. We are into the antennas MCQ series, which is part of EMFT, and in this particular channel, the Gate Conqueror channel, we had covered EMFT like never before. That I can guarantee here. That I can guarantee that we had covered EMFT like never before. That's for sure. If you consider the subject of EMFT, as you know, EMFT contains 5 modules. EMFT contains 5 modules. Module 1 elements of EMF theory. Module 1 is elements of EMF theory, which is common for both EC and electrical. For EC, of course, it is module 1, and for electrical, it is a complete syllabus. Very important module for both. Of course, for electrical, it is a complete syllabus. Naturally, it will be very important, right? Module 2 is EM wave propagation. Module 2 is EM wave propagation. Again, very important module where we try to understand what are EM waves and how the waves are propagating through different mediums like free space, materials, good conductors, good dielectrics, perfect dielectrics, and also we try to understand how the power is associated with a given wave by using Poynting theorem, and also we'll go through like concepts like wave polarization, how the wave is getting polarized and what determines the wave polarization and all, and also we'll see how reflection and diffraction of plane waves takes place when they are incident on some perfect dielectrics. So these kind of very important things, and under reflection and diffraction of plane waves, we'll also see terms like critical angle, total internal reflection, and Brewster angle. Very important for all the competitive exams, and already we have started a series on this EM wave propagation. Module 3 is transmission lines. Module 4 is waveguides. In waveguides, we have seen concepts like circular waveguides and rectangular waveguides. So we'll have some very important concepts like rectangular waveguides and circular waveguides, and there's a lot of connectivity or common points between these two waveguides. Like based on the geometrical structure, we actually divide these waveguides into rectangular waveguides and circular waveguides, and we have a lot of common thing in between these two. So we'll try to discuss what are the common things here and how the waves will propagate, what are the different types of modes, what is dominant mode, what is critical frequency, and all those very important things we try to discuss in waveguides. Module 5 is about antennas and optical fiber communication. And as I told you, optical fiber communication is a very small concept, very small part concept, where the syllabus is not greatly defined actually by GATE syllabi. So, of course, optical fiber communication is a very vast subject, but the syllabus given for GATE is very minimal. And antennas, of course, in antennas you have a good syllabi. And remember the speciality of our GATE Conqueror channel, especially this EMFT course, is that we cover for both GATE and ESC at a time. This is the uniqueness of my teaching. I don't only teach for GATE actually. I teach such that students who are preparing for GATE and students who are preparing for engineering services both are benefited at a time. So that's the important thing that you need to understand. So in these 5 modules, for this module 1, we had created a playlist. Already we had created a playlist for this module 1, and we have around 40 videos here with 50 hours of content. We have 40 videos and 50 hours of content. That's in module 1. And in module 2, this is completed actually. This playlist is completely done, which will be useful for both GATE and ESC. If you want, I'll add 100 or 200 practice questions. That's not a big deal for me. I'll try to add it, but there are so many number of questions here, which cover all previous year questions, all theory, derivations and all. I'll try to brief that what we have. Why I'm trying to brief it because all those who are newly joined for a particular channel, that is GATE Conqueror, for our particular channel, then those people need to know what is already there in this particular channel, so that this beautiful content will go up to the students, and students will be benefited by this particular content. In module 2, for module 2 also, we have created a playlist with 10 videos and 20 hours of content. Generally, elements of EMF theory, as far as I know, maximum number of hours they try to deliver on any YouTube channel, it will not be more than 10 hours. Maximum content is only 10 hours. But against that, what the number of hours that we created is just enormous, tremendous. Like 5-fold content we had created there. And transmission lines and waveguides we are yet to start. Antennas also we had created a playlist with the name of Antennas Mahamarathon. Antennas Mahamarathon. Here we had created something around 18 videos with 38 hours of content. This too, dear, I can say the name also suggests it is a Mahamarathon, really. Like on antennas, I'd seen maximum YouTube content will be around just like around 8 hours, not more than that. But this content is very much large. Like we have 18 videos and 38 hours of content is there on this particular Antennas Mahamarathon series, and I'm willing to add 2 more videos to this, where some previous year questions and some very special practice questions I want to add. So that also I'll try to do, nothing to worry about that. Already you can see there's a lot of scope here for your learning. In module 1, almost like we have 50 hours of content already available on our particular channel. And for module 2, already 20 hours of content is available. And still a small part of this module 2 is left out, which we are doing with parallelly along with the MCQ series. And for module 5, we have around 38 hours of content. Almost like you can say we already have like 108 hours of content. It's really a huge number, I'm right? And I'm ready, I am ready to take 112 more hours of content covering module 3, module 4, OFC, and a small part which is left out in EM wave propagation. So this will be like never before. 220 hours of content will be available only on EMFT. Now you tell me, are we not covering comprehensively? Absolutely. We are trying to cover the syllabus comprehensively, and there is no doubt about that. There is no doubt about that. Any doubts, please let me know, dear. Any doubts, please let me know. Yes. Anyone, any doubt? Please let me know. Fine. Okay then, good. So we'll go for module 1. We'll see what you have in module 1 or what we had covered in module 1. In module 1, we had covered elements of EMF theory. Elements of EMF theory. Basically, elements of EMF theory is the basic unit for all complete EMFT, and electrical people mostly concentrate on this particular module, which is the complete syllabus for electrical and module 1 for EC. So what we had covered in elements of EMF theory, let me explain. So for understanding EMF, basically what is required is strong basics are required. If you want to understand EMF, the main thing is we need some strong basics. Without basics, I'll tell you one thing here. Why students feel that EMF is very difficult? Basically, students feel EMF is very difficult because most of them, I can say, not all of them, but most of them, they actually lag in basics. Because that they are lagging in basics, and this particular subject actually requires very strong basics. Because that these people lag in basics, for them it looks like it's a very difficult task. But actually, once you are okay with these basics, then it's a very simple subject. That is what I strongly believe. So what I had done is, like, before starting or rushing through what you call module 1 or elements of EMF theory, what I had done is I took some classes on basics of EMF theory, where on basics like around 15 hours we had covered only basics. That's the highlight of this particular module, I can say. That is the highlight of this playlist, because no other playlist, I can guarantee, no other playlist will have content like this. We have some enormous content here. We have some enormous content which includes these basics. Okay. So what we had covered under basics, let us see. What we had covered under basics. Okay, I divided these basics into two parts. One, elements of vector calculus. Elements of vector calculus. This is what we had covered. Yes. Yeah. This is what I had covered. Elements of vector calculus in the first half. In the second half, we had covered coordinate system. Coordinate system. What we concentrated in the first module, that is I can say the first part of the basics, which is elements of vector calculus, is in elements of vector calculus we covered concepts like scalar. What is scalar, dear? A scalar is something which has only magnitude and no direction. and such quantities are called as scalars. Of course, if you want to take some examples, you can take distance, time, speed, and all these things are scalars. If you try to take some electrical quantities, then you can say voltage, current, and all these are some what you call the scalar quantities. Okay, definitely, dear. Actually, due to some technical problem, I had not able to start the other theory. I will try to complete this week, Amit. Don't worry, dear. This week I'll try to complete. Okay, that's fine. That's fine. And this week, anyways, I'll try. I'm going to complete the complete theory of EM wave propagation. Don't worry. Don't worry at all. That I guarantee. That I guarantee. Nothing to worry. Okay. So that we are done in scalar and in vector. A vector is one which is having both magnitude and direction, and you can take examples like velocity, acceleration, and so on. Okay. Yes, Siddhant Saga. It is K. Rao, sir. Sir will be coming. Sir will be coming. Just have some more patience. Okay. Amit. Okay. Okay, Amit. Now you can see why basics are important. Can I ask you a small question, Amit? What can I answer, dear? Sir will come online very soon, okay? Very soon, sir will come online. Transmission lines is not left, dear. Oh, this month is March, no? By end of April, you take my word. I'll complete EMFT, okay? Take my word, Amit. I'm going to finish complete EMFT by this particular month, that is April, okay? We have so many months still left out. We have like, you have 9 months. You'll have solid 9 months for your preparation, because before 9 months I'm completing GATE 2023. Transmission lines and waveguides will take parallelly, okay? Don't worry. So, okay, Amit, what I want to ask you is, are you able to hear me? What I want to ask you is, one second. Sorry, small disturbance. Okay, fine. So, what about current, Amit? Current, is it scalar or vector? Current, is it scalar or vector? Yes, Amit. Current is scalar. Wonderful, wonderful, wonderful. Why so? Current, does it not have direction? Current is having direction, no? Then why it is scalar? When current is having direction, then why it is scalar? See, just think that this is the interview question that you are facing, Amit, and your interviewer is asking why current is scalar. It is having magnitude and direction, no? This is the same question you had asked in your interview. Then how do you answer? That is how these things are very, very important here. These things are really very, very important. How do you answer? Okay, Amit. how do you answer? See, the current is scalar. You can Google it, no problem. But he's asking why current is scalar. Current is having magnitude and direction, no? He's asking why current is scalar. Can you answer? See, anything that is having magnitude and direction is vector, no? Current is also having magnitude and direction. Then why current is scalar? Why not it is vector? Any strong reason? Any strong reason? See, all this very interesting concepts I covered in elements of EMF theory. You can just go through that, okay? Like every number is scalar is constant at every point. Okay, but see, you are saying current is scalar, no? Yeah, I understand, but you are saying current is scalar, no? When you are saying current is scalar, I am asking why current is scalar. It is having both magnitudes and direction, no? Oh, very good. You watch my lectures, then you must answer, okay? See, that is what interviewer will expect from you people, that you answer in simple words. See, I'll answer it in simple word. Current is scalar despite having magnitude and direction, because every vector is one which obeys vector addition, and current is someone who will not obey vector addition. Therefore, even though it is having magnitude and direction, it is a scalar quantity. Am I clear? Am I clear on this? Such kind of discussion, such kind of definitions, such kind of standard learning we can find on this Get Conqueror channel. Then we have discussed about basic concept, unit vector. Basically, unit vector is something which gives you direction, okay? Current is dq by dt, ratio of two scalar is scalar. Of course, I too defined it in that way. But not always, okay? But not always. The actual reason is it does not obey. It does not obey vector addition. Scalar by scalar need not be scalar. Scalar by scalar need not be scalar always. Okay. Then if current density, if you take it is current per unit surface area, then current is scalar and surface area is scalar. Then in this case, you should have both scalars, right? But current density is vector. No. Transmission lines are not covered, Karna. Karna Reddy. Transmission lines are actually not covered previously. We'll try to cover it in this particular series. Of course, surface area is vector, but when you take current density, then it is current per unit surface area. Okay, that the area, surface area, direction is what current density is taking. Surface area direction is what current density is taking actually. Okay, that's fine. So what? Only simply that current is current I is equal to dq by dt, rate of change of charge. Both are, this charge is scalar and time is scalar. That does not ultimately mean that current will also be scalar. That is what I am trying to tell you, Amit. That's not the actual reason, okay? That's not the actual reason. The actual reason is something different. That is from the basic definition of vector, because by the basic definition of vector, it says that it is one which is having both magnitude and direction, and it is one which obeys vector addition. Got it? So after we are done with scalar, vector, unit vector, we went through addition of vectors, we had gone through parallelogram law, and head to tail rule. Head to tail rule is also called as triangular law. Head to tail rule is also called as triangular law. Thank you, Amit. So we have seen these two kinds of laws, parallelogram law and head to tail rule, and some wonderful discussion we have done on this. You can please go through that particular series where you can find this addition of vectors. Then we went for basic laws of vectors. What are basic laws of vectors? Can anyone tell me? Amit, Karna, anyone? What are basic laws of vectors, dear? Can anyone tell me? Yes, anyone? What are these basic laws of vectors? Basic laws of vectors. Anyone? What are basic laws of vectors? Commutative law. Associative law. And distributive law. Commutative law, associative law, and distributive law. Again, you have commutative law of addition and commutative law of multiplication, associative law of addition and associative law of multiplication, distributive law of addition and distributive law of multiplication. If you want to go in detail of these laws, then you have commutative law of addition, commutative law of addition. That if A and B are two vectors, A plus B is equal to B plus A. This is commutative law of addition. And if you want to go for multiplication, if K is a scalar and A is a vector, K into A is equal to A into K. That's commutative law of addition, and this is commutative law of multiplication. Associative law of addition. If A, B, C are three vectors, A plus of B plus C is equal to A plus B plus C. That is associative law of addition. If K and L are two scalars and A is a vector, K into LA is equal to K into L into A. Then the distributive law. Distributive law of addition. K into A plus B is equal to K scalar, A and B are vectors. K into A plus K into B. Yes, now anyone can tell me what is distributive law of multiplication? Distributive law of multiplication, anyone? Distributive law of multiplication. Anyone? Amit? Anyone? Amit, Karna? Anyone? Distributive law of multiplication. Very interesting concept. Distributive law of multiplication. Anyone? There was some other person, no, Amit? He was just asking about K. N. Rao sir and he just left. Think. Distributive law of multiplication. Think, everyone. Think and tell me. Distributive law of multiplication. This is where our particular subject in Gate Conqueror channel will become very special, because this is not any ordinary stuff that we had delivered on our particular channel. This is a real champion content we have done. Lot of strain that we took from all these years. We tried to kept it on this particular playlist so that students will be of maximum benefit. Anyone think and tell me? Very interesting question actually. What is distributive law of multiplication? Distributive law of multiplication. Anyone? There is nothing like distributive law of multiplication. This is what you need to understand. Because distributive property is already used in addition. This kind of strong basics is what even organizations like BARC and ISRO will look for. Concept is very, very important here. Now, when I say basic laws of vectors, you might have thought that what is there in this basic laws of vectors? They are all very simple. But as we had went through this, you might have understood basic laws of vectors has so much of concept into it, right? Then we had went through multiplication of vectors, In multiplication of vectors, we had seen dot product, scalar product, cross product or vector product, cross product or vector product, and here dot product, scalar product, something where the resultant is a scalar quantity, and of course cross product or vector product is a concept where the resultant is a vector quantity. Thereby the names are dot product or scalar product or cross product or vector product. Then also we had seen dot product obeys how many basic laws like commutative, associative, distributive, and also we had seen what you call cross product obeys how many basic laws. I hope you are very clear with this dot product and cross product concept. I'm right. Dot product of two vectors, if you take it is something like a dot b is equal to sorry dear, a dot b is equal to mod a mod b cos of theta ab, cos of theta ab. This is when angle theta ab is given. Theta ab is the small angle between a and b. Okay, and if you are given vectors like this, a is equal to ax plus ay plus az, b is equal to bxax plus by plus bzaz, then in this case a dot b will be equal to ax bx plus ay by plus az bz. Sorry. Yeah. Ax bx plus ay by plus az bz. This is when angle is not given, and this is when angle is given. What I am asking you is, dot product obeys how many basic laws? Can anyone answer? Anyone? Amit, Karna, anyone dear? Try to answer this basic question. Dot product obeys how many basic laws? Dot product obeys how many basic laws? Anyone? Anyone, please let me know. These are all very simple things, I'm right. Let me start with commutative. Whether dot product obeys commutative law, anyone? Commutative law means a dot b is equal to b dot a. Commutative law means a dot b is equal to b dot a. Yes, they are equal. Therefore, it obeys commutative law. Next. Associative. Whether it obeys associative law, whether it obeys associative law. What is associative law? A dot B dot C is equal to A dot B dot C. Now you tell me, someone please tell me whether it obeys associative law or not. Whether it obeys associative law or not. Simple question. Whether it will obey associative law or not. Tell me, dear. Whether it will obey associative law or not. Okay, just tell me, can I say A dot of B dot C is equal to A dot B dot C? Can I say A dot of B dot C is equal to A dot B dot C? Anyone? You cannot say, I'm afraid. I'm afraid that we cannot say. Why? Because B dot C, this dot product of two vectors, will result in a scalar quantity. This will result in a scalar quantity. Once you have this scalar, then product between vector and a scalar, not possible. That means what? Writing itself is absurd. Leave about following A dot of B dot C, not defined. So dot product does not obey associative law. So many students, when I ask this question, they get confused. So that's the reason why I recommend you to have very strong basics. And if you go for distributive law, distributive law, whether it obeys distributive law or not, anyone? A dot of B plus C is equal to A dot B plus A dot C. Yes, true. It obeys distributive law. Therefore, dot product obeys commutative law and distributive law. Commutative law and distributive law. Clear? Is this clear? Now you tell me, cross product. Or called vector product. If A and B are two vectors, A cross B is equal to mod A mod B sin theta AB. Theta AB is a small angle between A and B into An. What is this, dear? This is magnitude. What is this, dear? This is direction. This is magnitude and this is direction. This is when angle is given. When angle is not given, given is A is AX AX plus AY AY plus AZ AZ, B is BX AX plus BY AY plus BZ AZ. A cross B, when angle is not given, is a determinant of unit vectors AX, AY, AZ, the coefficients of the first vector, very important. AX, AY, AZ, coefficients of the second vector bx, by, bz. This is how you try to solve it. By using determinant, we try to find the cross product. This is when angle is given, this is when angle is not given. Now you tell me, cross product obeys how many basic laws? Anyone please? Anyone tell me? Sorry. Cross product obeys how many basic laws? Yes, dear. Just tell me, cross product obeys how many basic laws? Very interesting concept. Most of them feel that they know everything about EMFT, but when I travel pan India, previously when I used to travel pan India, I used to experience this thing that people think that okay, this is very easy stuff, like it is very easy thing to understand. All these are very simple thing, dot product, cross product. But you know, you don't believe this if I tell you, more than 60 to 70% of the subject EMFT depends on how in depth you understand these basic products or these basic terms like dot product and cross product. That's very, very important actually. Yes, so many are online. Anyone please tell me? Anyone, can you please tell me? Cross product obeys how many basic laws? Anyone? Amit, Karna, anyone? Think and tell me. Don't be in a hurry. Think and tell me. Cross product obeys how many basic laws? Yes? Cross product obeys how many basic laws? Commutative, will it obey? Anyone? Will it obey commutative law? If cross product is obeying commutative law, A cross B is equal to B cross A. Can anyone tell me? Is it equal? Is it equal, anyone? Can you tell me, is that equal? A cross B is equal to B cross A. Is that equal? Anyone? Not equal, correct. It's not equal. That means what? It is not commutative. One thing is clear. Cross product is not commutative. But A cross B is equal to minus B cross A. Therefore, it is called as anti-commutative. That's why it's very important. That is the reason why A cross B and B cross A are not equal. That is why it is very, very important that this vector is the first vector and this vector is the second vector. You must write in order. You cannot interchange them. Because when A cross B is equal to B cross A, you can interchange, but they are not equal, no? So you should not interchange them. And Amit, I have one more doubt here. Again, basic doubt, okay? In some books I had read like this. It is minus of B cross A. Which is correct here? Is this statement correct or this statement correct? Out of this both, which is correct? Out of these both, which is correct? Yes? Can you know the answer? Out of these both, which is correct? See dear, A is 2ax plus 3ay, okay? B is 3ax plus 2ay. If you do A cross B, two by two is enough. Resultant will be along AZ 2, 3, 3, 2. We wanted it to get 2 by 2, okay? So that it will be easy for our calculation. This is 4 minus 6 minus 2az. This minus 2az. Now if we do B cross A, determinant B, first vector 3, 2, 2, 3. This is, sorry, sorry, yes, you are correct. What is this? 4 minus 9, am I right? Minus 5az, this is 3 into 3, 9 minus 4, this is 5az. So very clearly, A cross B is not equal to B cross A, there is no doubt. Because A cross B for answer you got minus 5az, B cross A you got 5az. How they will become equal? How they will become equal? A cross B is equal to, how they will become equal? Minus of B cross A. Now you know B cross A is 5az, minus of B cross A, minus 5az. They both are equal. That means this is correct. This is correct. A cross B is equal to minus of B cross A. A cross B is equal to minus of B cross A. This is the correct answer. Do you agree, everyone? Do you all agree, everyone? Do you all agree? That means Karna minus B cross A is wrong. Minus B cross A is wrong. This is correct, okay. Okay, Karna. This is correct, okay. This is correct, okay. Is minus B cross A wrong? Shall we check? If this is B, what is minus B? Minus 3ax minus 2ay. If we do minus B cross A, determinant minus 3 minus 2, A is 2 and 3 of AZ, of course. This minus 9 plus 4 minus 5 AZ minus 5 AZ minus 5 AZ. That means what? Minus of B cross A and minus B cross A are both are same. Both are same. This is also something so many people don't know. They both are same. Got it? So these both answers are same. It is not commutative. It is anti-commutative. It is not commutative. It is anti-commutative. associative, 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 A cross of B cross C is equal to A cross B cross C. Is it equal, anyone? Is it equal, anyone? Okay, previously A dot B dot C is equal to A dot B dot C. We are not able to write because once we have done A dot B, we got a scalar quantity, and we cannot do dot product with this one scalar and one vector. That was the problem, okay. But here there is no problem because A cross of B cross C. B is a vector, C is a vector, B cross C is one more vector, something like D. A cross D possible. In first place, the product is possible. But listen carefully, what I am asking is there, are they equal? Are they equal? Are they equal? Here also, dear, so many people say they are equal, but it is not equal. We don't have that much of time to verify here. Please take some example and verify. They are not equal. So it is not associative. It is not associative. Is it distributive? Is it distributive? Of course it is distributive. A cross of B plus C is equal to A cross B plus A cross C. It is distributive. Thank God. It is obeying some rule finally. It is distributive. This is about multiplication of vectors. This multiplication of vectors, dot product and cross product. Del and its properties. As you know, del is a very special quantity here. Out of all the quantities, del is very special quantity, and we had discussed, we had some very wonderful discussion on this del quantity. Del, its symbol is reverse of delta. In Cartesian coordinate system, it is given by dou by dou x of ax plus dou by dou y of ay plus dou by dou z of az. This is del, which is also called as a vector differential operator. Vector differential operator, also called as spatial derivative operator. Vector differential operator or spatial derivative operator. Can anyone tell me why it is spatial derivative operator? Why it is spatial derivative operator? Anyone? Why it is a spatial derivative operator? It is called as a vector differential operator or spatial derivative operator. Firstly, dear, why vector differential operator? It is called vector differential operator because it is a vector in itself. You can see there are unit vectors ax, ay, az. It is doing differentiation dou by dou x, dou by dou y, dou by dou z. That's why it is called vector differential operator. As the derivative is done with respect to space coordinates x, y, z, it is also called as spatial derivative operator. It is also called as spatial derivative operator. It's a very, very important operator, dear. When this operator is used upon a vector using a dot product, what it is called here, anyone? What is this del dot A called? What is this del dot A called? Anyone? What is this del dot A called? Anyone? Del dot A is called divergence of A. Del dot A is called as divergence of A. Del is a vector, A is a vector. Del dot A is called divergence of A. Fine. Del is a vector, A is a vector. If you operate cross product between them, then what it is called here? What it is called? If you operate it over a cross product, then what it is called? Del cross A is called curl of A. Curl of A. Del is directly operated on a scalar. What it is called here? Gradient of a scalar. Do anyone remember what is gradient of scalar? Gradient of scalar V. Do anyone remember what is gradient of scalar V? Gradient of any scalar. What it is, dear? Gradient of any scalar. What it is? Gradient of any scalar. Gradient of any scalar is a vector quantity. Divergence of any vector, what is the resultant? Scalar quantity. Curl of any vector, it's a vector quantity because del is a vector, A is a vector. So these are the three important operations here. Del operated with the dot product over a vector, del operated over or cross product over a vector, and del directly operated on a scalar. Gives you divergence, curl and gradient, and some very important properties because everything in EMFT will revolve around this del operator. If you take for example Maxwell equations, if you remember, what are Maxwell equations, dear? Maxwell equations for static fields. If you take what is Maxwell first equation? It is from Gauss law, and what is the differential form? Del dot D is equal to rho V. Now you can see divergence concept came into picture. If you take Maxwell's second equation, what it is? Del cross E is equal to 0. Now you can see this curl concept came into picture. Maxwell third equation, del cross H is equal to J. Again you can see the curl concept came into picture. The curl concept came into picture. Fourth equation, del dot B is equal to 0. Again divergence concept came into picture. That's why, like Maxwell equations are those which actually govern. Maxwell equations are those which actually govern this static field theory and time varying field theory, or elements of EMF theory. And in each of these Maxwell equation, you can see del is present. Now you tell me, if you are not sure of what del is doing there, is it possible for you to understand EMF subject? So many people just try to buy hard this particular formulas, uh, doing that it will be very very difficult. It will be very very difficult for them, dear. It's not easy. It's not easy. Without all these basics, it is not going to be easy. So this is what we study, and along with that, we'll study vector identities, which is nothing but divergence of curl of any vector is 0, curl of gradient of any scalar is 0. Along with that, in this concept, we'll also study vector identities. Vector identities. This will complete the first part of basics. Just overview I'm trying to give. Elements of vector calculus is done in basics. What are vector identities, dear? What we study under vector identities? Under vector identities, we study the first one, divergence of, that means del dot divergence. Divergence of curl of any vector is 0. Curl of, that means del cross, curl of gradient of any scalar is 0. These are vector identities. These are two major vector identities that we'll go through, and of course we'll also go through back minus cap rule, which is the vector triple product. A cross of B cross C is equal to B into A dot C minus C into A dot B. This is back minus cap rule. This is back minus cap rule, which is vector triple product. And also we see something like del dot AV. Del dot AV, A is a vector, V is a scalar. Del dot AV is equal to A dot del V plus V into del dot A plus V into, plus V into del dot A. We see something like this. Yes. Okay. Del cross AV will be del V cross A plus V into del cross A. Just we can go through all these vector identities here. That is what we had seen in the first part, that is elements of vector calculus. In coordinate system, the second part, in coordinate system, we had seen types of coordinate systems, in which we had seen Cartesian coordinate system, cylindrical coordinate system, and spherical coordinate system. Okay, can anyone tell me what are the coordinates of Cartesian coordinate system, dear? What are the coordinates of Cartesian coordinate system? Anyone? What are the coordinates of Cartesian coordinate system? Anyone? 1 second here. Yeah. What are the coordinates of Cartesian coordinate system? Anyone? Cartesian coordinate system, coordinates x, y, z. Cylindrical coordinate system, coordinates rho, phi, z. Spherical coordinate system, coordinates r, theta, phi. And what are these limits? Limits of x, y, z. Minus infinity to plus infinity. Limit of x, limit of y, and limit of z. Each moving from minus infinity to plus infinity. These are for Cartesian coordinate system, very simple one. And this is cylindrical coordinate system. Coordinates rho, phi, z. Rho limit 0 to infinity. Phi limit azimuthal angle 0 to 2 pi. Z limit same, minus infinity to plus infinity. Rho, phi, z. R, theta, phi. R, theta, phi. R limit radius of sphere 0 to infinity. Theta co-altitude angle limits 0 to pi. Phi limits 0 to 2 pi. Phi limit 0 to 2 pi. Zero to 2 pi. Clear? Yes, we have seen the types of coordinate system. Then we have seen their coordinates, their ranges, and we have seen a concept called point transformation. Big concept, very big concept. Point transformation. How to convert a point from one coordinate system to another coordinate system. I request you all to go through the playlist so that you will get a better understanding of this particular topic, point transformation. Then we had seen differential length, differential surface, and differential volume presentation in all coordinate system. Then we had seen divergence, curl, gradient, and Laplacian in all coordinate system. That is also truly wonderful topic dear. Divergence, curl, gradient, and Laplacian. Trying to write in all coordinate systems is really very interesting concept. You can just go through it, and this particular thing requires so much of basics. Okay, so once you go through these basics, and if you go through this divergence, curl, gradient, and Laplacian, truly you will start enjoying this particular subject. So that is what we try to learn from the basic concepts. Okay, so in module 1, elements of EMF theory, before actually I start the elements of EMF theory, which includes static field theory and time varying field theory, before I actually start, what I do is I explain all these basics with lot of pain. So many hours we try to spend on this, and we try to learn all these basics. Once all the basics are done, then it looks very simple. We enter into elements of EMF theory with electrostatics and magnetostatics at the handing of static field theory. again subdivided, static field theory. It is study of static fields. Static field theory. In static field theory, what we study is, we study about electrostatics and magnetostatics basically. And magnetostatics. What we study in this electrostatics is this electrostatic field is because of the static charges, and magnetostatic field is because of uniform motion of static charges which is producing DC current. Under electrostatics concept, we study two Maxwell equations, and magnetostatics we study two Maxwell equations. Putting together, we get Maxwell equations for static fields. Maxwell equations for static fields. In Maxwell equation for static fields, under electrostatics, we derived equation number 1, integral form, closed surface integral of d dot ds is equal to volume integral of rho v dv. True form, psi e is equal to charge enclosed. There is an integral form. Differential form, del dot d is equal to rho v. Source, Gauss law for electric fields. Gauss law for electric fields. Second one, closed loop integral of E dot dl is equal to 0. Differential form, del cross E is equal to 0. Source, conservative property of electric field. Third mantra, closed loop integral of H dot dl is equal to I enclosed, or which is equal to surface integral of J dot ds. Surface integral of J dot ds. Integral form, differential form, del cross H is equal to J. Source, Ampere's law. Fourth one, closed surface integral of B dot ds is equal to 0. Differential form, del dot B is equal to 0. Source, Gauss law for magnetic fields. Gauss law for magnetic fields. So in this, the first two equations are from electrostatics, the last two are from magnetostatics. Therefore, put together, this is called Maxwell equations for static fields. Any doubts here? Any doubts, please let me know. Any doubts, please let me know, dear. Any doubts, please let me know. Sorry. Yeah, that was under electrostatics, and this is under magnetostatics. Put together, we have derived Maxwell equations for static fields. Other than this, we have derived very important Poisson's and Laplace equations. We have derived boundary conditions. In boundary conditions, we have derived dielectric boundary conditions and dielectric conductor boundary conditions, and dielectric conductor boundary conditions. And in these boundary conditions we derived ET1 is equal to ET2. Tangential component of electric field is continuous across the boundary of discontinuity. Then dN1 is equal to dN2, or dN2 minus dN1 is equal to rho s. This implies, what is rho s there, dear? Rho s is the charge that is deliberately placed on the boundary. Therefore, when the charge that is deliberately placed on the boundary is becoming zero, then normal component of electric flux density is continuous across the boundary of discontinuity. So dN1 is equal to dN2. Similarly, HT2 minus HT1 is equal to K cross AN. This is in vector notation. In scalar notation, we can write HT2 minus HT1 is equal to K, where K is the surface current that is deliberately placed on the boundary. If that surface current is zero, then we can write HT1 is equal to HT2. HT1 is equal to HT2. Similarly, BN1 is equal to BN2. BN1 is equal to BN2. This is unconditionally continuous. This is unconditionally continuous. BN1 is equal to BN2. And the magnetic field are conditionally continuous. They are continuous if and only if K is 0. Clear? And we have discussed about these boundary conditions. Then we have discussed about capacitors and inductors. Capacitors and inductors. Again, types of capacitances, types of inductances, with all derivations, theory about all this. Not just theory, dear, loads and loads of derivations were also done on this subject. Please just go through that particular module. Just go through that particular module. It will be useful for you people. Along with that, then we have derived Maxwell equations for time varying fields. In time varying fields, the second equation and third equation will vary. The second equation is from Faraday's law. The third equation is from Maxwell contribution. Maxwell contribution or inconsistency of Ampere's law. According to Faraday's law, induced EMF within any closed path is equal to rate of change of flux linkage. And Professor Heinrich Emil Lenz, what he had done is he had introduced the negative sign. So that was from there we got this Faraday's law. And according to Faraday's law, del cross E is equal to minus dou B by dou T, closed integral of E dot dl is equal to surface integral of minus dou B by dou T dot ds. This looks good. This integral form, and differential form is del cross E is equal to minus dou B by dou T. That is time varying field form. In time varying field, and if you consider the Maxwell equation or the Maxwell contribution for this, then differential form is del cross H is equal to J plus JD. Del cross H is equal to J plus JD. Integral form, closed loop integral of H dot dl is equal to surface integral of J plus JD dot ds. Clear? So we got these two equations that will be replaced here, which will complete Maxwell equations for time varying fields. Completes Maxwell equations for time varying fields, and some more problems on that. That we can do very easily. That thing we can do very easily. That's a very important module dear. Static field theory, and this is time varying field theory. All these derivations by default I believe that you know. So if at all you had forgot any equation, just you can go through this particular series of the playlist, with the playlist of 40 videos and 50-hour content. Some exclusive content is there on the channel dear. This was about module 1. Then I started with module 2, EM wave propagation. That's the next one. EM wave propagation.